AB Calculus, section 3.10 on derivatives of inverse trig functions and the general inverse function. Before I get into the formal set of notes, what I wanted to do is use implicit differentiation to show you how you'd find the derivative of a couple of the inverse trigonometric functions. I'm not going to be finding the derivative of inverse cosine of x, at least on this slide, but I will show you what that is on the next slide. So here I've sketched the inverse sine function in the form of a right triangle. Right? So if y, an angle, equals the inverse sine of x, then a right triangle with an acute angle of y would have a sine of x over 1. Now, I don't know how to find the derivative of inverse sine of x in this form, but if I rewrite this in the form sine of y equals x, that's an equivalent form. Now I can differentiate both sides of this equation using implicit differentiation. So the derivative of the left side will be cosine of y times y prime. Derivative of the right side will be 1. Therefore, y prime will equal 1 over the cosine of y. Now, in order to find the cosine of y, I've got to go back to my triangle, and I've got to find the adjacent side over the hypotenuse. Therefore, what I'm going to do is use the Pythagorean theorem. If I use the Pythagorean theorem with a squared plus b squared is equal to c squared, I can solve for a. So a squared would be 1 minus x squared, and a would be the square root of 1 minus x squared. So if I were to find then the cosine of y, that would be the square root of 1 minus x squared over 1. Therefore, the derivative of the arc sine or inverse sine is 1 over the square root of 1 minus x squared. Okay, let's look at arctangent. Now, these forms are totally fine to write either as sine to the negative 1 of x or arc sine of x, like I have over here with tangent. Therefore, again, like I said, these are equivalent forms. And I would, of course, when deriving this, use the second form. So the tangent of y would equal x. Now, again, look at the image I've got here. The tangent of the angle y is x over 1. So I will eventually have to find the hypotenuse, which will be the square root of 1 plus x squared. Now, when we take the derivative of both sides implicitly, I would get secant squared y times y prime is equal to 1. And solving for y prime, I get 1 over secant squared y. Now, 1 over secant squared y is equivalent to cosine squared y. And now I can look up at my triangle. The cosine of y is 1 over the square root of 1 plus x squared. So if I were to square that expression, 1 over the square root of 1 plus x squared, and I squared that expression, I would get the derivative of arctangent of x, which would be 1 squared, which is 1, over 1 plus x squared. Okay, so the derivative of arc cosine is very closely related to arc sine. Its derivative is negative 1 over the square root of 1 minus x squared. It can be done in a very similar fashion to arcsine and arctangent, so you can try that one on your own. If you got questions, let me know. All right, now for the formal part of the lesson. Our goals for today are to know and be able to use the derivative of inverse trig functions and how to find the derivative of a general inverse function, given the original. So what are the derivatives of the following? We already talked about these, right? F prime is 1 over the square root of 1 minus x squared. For cosine, very similar. It'd be negative 1 over the square root of 1 minus x squared. Arctangent is 1 over 1 plus x squared. Now, what do you do if you've got a chain rule going on? You can see in parts B, D, and F. What do I do if I've got the inverse sine of g of x? Well, the derivative of f of x in that case would be 1 over the square root of 1 minus g of x squared times the derivative of g of x. And that's going to hold true for all three of these in a similar form. This will be negative 1 over the square root of 1 minus g of x squared times g prime of x using the chain rule. And then, of course, for arctangent of g of x, we would have, and I'm going to write it in a slightly different form, g prime of x over 1 plus g squared of x. Okay, let's look at a couple of examples. Example 1 and example 2. Example 1, we've got the inverse sine of x squared. So I am going to rewrite this in the form 1 over the square root of 1 minus, x squared squared times the derivative of x squared, which is 2x. So I could rewrite that in a much cleaner form as 2x over the square root of 1 minus x to the fourth. That would be the derivative of the inverse sine of x squared. All right, how about the derivative of arc cosine of square root of x? Okay, so arc cosine's derivative is negative 1 over the square root of 1 minus the function squared times the derivative of the inner function. So the derivative of this function, well, if x plus 1 is raised to the half, the derivative of that with respect to x would be 1 half x plus 1 to the negative 1 half. All right, so that's equivalent to 1 over 2 square root of x plus 1, and then of course I got to multiply by the derivative of x plus 1, which is 1. Okay, so as we simplify this, let's look at what's going to happen here. I'll get 1 minus, and this squared will just be x plus 1. So it'll be 1 minus the quantity x plus 1, which will be negative x. All right, so I'm going to have a negative 1 over, I'm going to bring this 2 out in front, the square root of negative x from this portion of the expression, and then the square root of x plus 1. That'll be the derivative of the arc cosine of the square root of x plus 1. All right, let's look at a third example, an AP example from a while back. Notice that if the function f is defined for all x greater than 0, and f of x equals x squared ln of x minus arctan x, find the limit as h goes to 0 of f of 1 plus h minus f of 1 over h. Well, this is equal to f prime at 1. So I got to find f prime first. F prime of x, we're going to use the product rule first. So that'll be 2x ln of x. So I took the derivative of the first, left the second alone, plus the first times the derivative of the second. Derivative of ln of x is 1 over x, minus the derivative of arctangent of x, which is 1 over 1 plus x squared. Now I'm not going to simplify. I'm just going to plug in a 1. So it'll be 2 times the natural log of 1 plus 1 times 1 over 1 minus 1 over 1 plus 1, which is 2. All right, natural log of 1 is 0. So I will get 2 times 0, which is 0, plus 1 times 1, which is 1, minus 1 half. Looks like that limit, which is equivalent to f prime at 1, will be a half. All right, so B. All right, let's keep moving on to the next slide. Okay, so next what I'd like to do is develop the equation for the derivative of any inverse function. So the general inverse function, okay? So first what I'm going to do, and I'm going to do this slightly different than the notes is telling us, I'm going to define y as the inverse of f of x. That means then that f of y is equal to x. And now I'm going to differentiate that with respect to x on both sides. So implicitly on the left and explicitly on the right, I would get f prime of y times the derivative of y, which is y prime. And that is what we're seeking, right? We're trying to find out what y prime is equivalent to. And of course, the derivative of x equals 1. So y prime is equal to 1 over f prime of y. Let's figure out what we're looking at here. So y prime is the derivative with respect to x of the inverse function. Okay, that's what we're trying to figure out here. Trying to find a general form for that. Now, y, we said, was equal to the inverse. So what I want on the right side then is the derivative, 1 over f prime of y, which is the inverse function. So it doesn't seem like it quite yet, but that is very useful when finding the derivative of an inverse function. So as you can see in conclusion, if g of x equals the inverse of f, then g prime is 1 over f prime of the inverse. So let's utilize that in an example below. Use the values of a one-to-one differentiable function in the table to compute the indicated derivatives or state that the derivative cannot be determined. Okay, the reason for the one-to-one differentiable piece is because when we talk about inverses, if a function is one-to-one, it passes the horizontal line test, which means that its inverse is also a function. So that's helpful. A detail that if you notice it, it really means that you understand what's going on. Okay, so let's talk about f inverse of 5. Well, I don't know what that equals, but I know that then f of that same value should equal 5. So I can locate where f of x equals 5 in the table right here. So that tells me f of 1 is 5, so f inverse of 5 is 1. So if f of 1 is 5, then f inverse of 5 equals 1. So when I'm looking for the derivative of the inverse at 5, I'm going to utilize the formula we just developed, which is f prime, 1 over f prime of f inverse of 5. F inverse of 5. That will be equivalent to 1 over f prime of f inverse of 5, which is 1. F prime at 1 looks to be 3/2, so the derivative or the slope of the tangent line to the inverse function at x equals 5 will be 1 over 3/2, which ends up equaling 2/3. Okay, so this we develop along the way using that general form of the derivative of an inverse. Okay, let's look at the second example. Switch up the colors here. What would f inverse of 2 equal? You can pause the video, think about that. Well, if f of -1 is 2, then f inverse of 2 is -1. So we would write the slope of the inverse function f of f inverse at x equals 2 would be 1 over the derivative of f evaluated at f inverse of 2, which is equivalent to 1 over f prime. F inverse at 2 is -1. The slope of f at -1 is 1/2. So that'd be 1 over 1/2. So the original, the derivative with respect to x of the inverse evaluated at 2 should be 2, which is 1 over 1/2. Okay, the final example. F inverse of 1 equals what? Well, as I look at the table, f of x does not have an output equal to 1. All right, so I'd be looking for the input such that the output of f is 1. Well, it doesn't look like I have enough information here because I have no output of 1. Doesn't mean it doesn't exist, just means not enough information. So we don't have enough information to complete part C. Okay, let's apply this to a free response question from back in the day. Okay, 2007, problem number 3. This would be a no calculator problem. We're given a table of values for f, f prime, g, and g prime. And we're told that the functions f and g are differentiable for all real numbers and g is strictly increasing. Now this piece likely is for a part of the question we're not going to use, or not going to be doing, but it's you'll start to catch on to the important information as you read these problems based on what we already know. The table above gives values of the functions and their first derivatives. The function h is defined as h of x equals f of g of x minus 6. Explain why there must be a value r for r between 1 and 3 such that h of r equals negative 5. Okay, so this is screaming intermediate value theorem. Okay, if on an interval we want to know that there is at least one value for r such that h of r equals negative 5, intermediate value theorem 99.9% of the time. Okay, so as we look at this, the first thing we need to do is we need to show that h of x is continuous. So since f of x and g of x are continuous on the real numbers, then f of g of x will also be continuous on the real numbers. Therefore, h of x is continuous on the real numbers and thus on the interval from 1 to 3. Okay, so we know that h of x is continuous. That was the first thing we needed to show to use the intermediate value theorem. Number 2, we needed to find the outputs of the endpoints. So h of 1, I'm going to plug h of 1 in. So h of 1 will equal f of g of 1 minus 6. Okay, so g of 1 looks to be 2, f of 2 is 9, and 9 minus 6 is 3. So h of 1 is 3, all right, which is good because that's an upper bound for h of r, which is negative 5. h of 3, I'm hoping, is going to be less than negative 5, which will be f of g of negative 3 minus 6. F of g of 3, not negative 3. G of 3 is 4. F of 4 is negative 1, and negative 1 minus 6 is a negative 7. That's great. Okay, so just a general sketch of h of x, right? I don't know exactly what it's going to look like, but I know that h of 1 is, 3. And I know that h of 3 is equal to, not to scale clearly, negative 7. So I know that there has to, I don't know what the function is going to look like. Maybe it looks like this. I don't know. But I know that there has to be an r value such that h of r equals negative 5. Okay, intermediate value theorem at its purest form. Okay, so part 3, I'm going to write a justification statement. So since h of x is continuous on the interval from 1 to 3, and h of 3 is less than negative 5 is less than h of 1, then by the intermediate value theorem, there exists an r value where r is between 1 and 3, such that h of r equals negative 5. Okay, there you have it. The first part, we showed that h of x was continuous. The second part, we found the outputs of the endpoints. And the third part, we justified it using the definition of the intermediate value theorem. Okay, we're going to do part D. Parts B and C probably had something to do with the strictly increasing portion of g of x. I'm not sure. but let's work on part D. So it says, if G inverse is the inverse of G, write an equation for the line tangent to the graph of G inverse at x equals 2. So what I need, like we know, if we want a tangent line, is I need a point. So I need to know G inverse of 2. Well, I can find that by finding G of what input gives me 2. So I look at G of x, looks like G of 1 is 2, therefore G inverse of 2 is 1. Now I also need a slope. I want the slope of G inverse located at x equals 2. That will be equal to 1 over G prime of G inverse of 2. All right, so G inverse of 2 we said was 1. Okay, so G prime of 1, let's see what G prime of 1 is, it's 5. Therefore, our slope is equal to 1/5. So I can write the equation of the tangent line to the graph of G inverse at x equals 2. That's y minus 1 is equal to 1/5 x minus 2. There you have it. Awesome. This was one of the most challenging, I think the lowest average for any FRQ. Of course, we only did A and D, but in a long, long time. I think the average out of 9 points was something like 2, maybe even less than that. Okay, example number 6. Example number 6 is a calculator allowed question. So the first thing I would do is consider y1 and y2 in your y equals screen, but it looks like functions f and g are defined as the following. What is the approximate value of x for which the derivatives or the slopes are equal? So in y1, I would put f prime of x, and in y2, I would put g prime of x. And you could do that in a couple different ways. You can manually find the derivatives. So f prime of x, what I mean is f prime of x is negative 2 over x cubed, and g prime of x is 1 over 1 plus x squared. So you could input those in for y1 and y2, or in y1 you could put math 8, and then in for that put 1 over x squared, and then it comes up with this like x equals, right? And when you populated, we've done this many times, but when you populate this automatically populated. You also want to put an x here, because what it does is then it develops a function such that it finds the derivative for all x values. Okay, and then do the same thing for y2 with g of x. Okay, but anyways, I digress a little bit there. When I graph the derivative of f prime, it looks like this and like this. Okay, and then when I graph the derivative of g prime, it kind of looked like this. All right, so I looked at my calculator and I said, oh, well, those slopes will be the same at whatever this value is. And that value ended up being C, negative 2.359. Okay, guys, we got one more slide here. It's just a quick one on reviewing some differentiation rules, and then that'll be it for 310. All right, a bunch of the differentiation rules. Yeah, so I'm just going to write these in. You can pause it and try these on your own if you'd like. All right, so x to the nth derivative is nx to the n minus 1. Sine x's derivative is cosine. Cosines is negative sine. Tangent is secant squared. Cotangent is negative cosecant squared x. Secant is secant x tangent x. Cosecant is negative cosecant x cotangent x. E to the x is great. A to the x is ln of a times a to the x. Natural log of x is 1 over x. Log base b of x is 1 over x ln of b. Inverse sine of x is 1 over the square root 1 minus x squared. Inverse cosine is negative 1 over the same. Inverse tangent is 1 over 1 plus x squared. All right, and then you got some composite rules. This would be n times f of x to the n minus 1th times f prime at x. Ooh, this is going to get annoying. This will be cosine of f of x times f prime at x. This will be negative sine of f of x times f prime at x. Using the chain rule, obviously. We would have then secant squared f of x times f prime x, and negative cosecant squared f of x times f prime of x. I'm just carrying that chain rule along. This would be secant f of x tangent f of x times f prime at x. This would be negative cosecant f of x cotangent f of x times f prime at x. This would be e to the f of x times f prime at x. This would be ln of a times a to the f of x times f prime at x. This would be 1 over f of x times f prime at x. Notice the parentheses. This would be 1 over f of x times ln of b times f prime at x. This would be 1 over the square root of 1 minus f of x squared times f prime at x. Negative 1 over the square root of 1 minus f of x squared times f prime at x. Oof. And then, of course, the last one, inverse tangent of f of x, would be 1 over 1 plus f of x squared times f prime at x. Okay, oof, that's a lot of stuff. All right, guys, that's 3.10. We'll see you in the next video.